Well, looks like we can start. Welcome back, everyone. We have our third exam returned. I was able to get it graded a little bit earlier this time. And the scores came out pretty nice on this one. The average score was 80.8%. A maximum score of 100% was obtained on this one. And two other exams were pretty close as well. So congratulations on getting through the third exam. We're pretty much almost done with the semester. With week 13 we're on. Next week is going to be a break week. And this is what we have going on for the remaining weeks. So this week here, 14, is just going to be an ordinary week. Then on week 15, Monday, we're going to do a full day, but possibly wherever we end up on Monday. Wednesday, we might start converting over to reviewing, and Thursday is going to be a full-on review week as well. Also, during this holiday where we're going to have the whole week off next week, that's a well-earned break for us. Part of what I'm going to be working on is getting the information filled out here on the final exam itself for finals week. I'll be posting the coverage. It's going to be a comprehensive exam, but I'll be specific. It's going to also include the sample exams that we mentioned before, and also get everything posted up here over the Thanksgiving break. But any questions or comments at all, folks, before we get started today? Trying to get that back where it was. There you go. Okay, well, just like with the other exams, the solutions are also posted here on the Canvas webpage. So if you'd like to take a look at them, then you could do so. You could see how different takes might look, or maybe just get a different clarification based on what comments I made on your exam. So here's where we left off next in section 15.1. This was a week ago today, so it feels like kind of a long time. So let's refresh ourselves just a little bit on what we were doing. In 15.1, or chapter 15 entirely, we're still doing inferential statistics. This will be our last chapter for the entire semester. And we're turning to a new concept, hypothesis testing. There's two hypotheses that we're going to be considering. A so-called null hypothesis, denoted H naught. It's a claim that's initially assumed true. And an alternative hypothesis, HA, the competing claim about the parameter. The analogy that we mentioned from our court of law is a null hypothesis in actual real court, if you're ever defending yourself, is that the defendant is not guilty. And the first thing that the court of law assumes is that null hypothesis is the actual truth of what's going on. The alternative hypothesis is the competing claim that someone is guilty in a court of law. And for just a really kind of silly example or a quick scenario, we said Mike is summoned to traffic court for speeding in a 35-mile-per-hour road. In a court of law, the null hypothesis is that my average speed, mu, is 35 miles per hour. That's just the statement that I am assumed to be innocent in this case. We assume that that's true as the law proceeds. But the statisticians, the actual researchers, are trying to show the alternative is true. This is the role that the prosecuting attorney would play. They start collecting evidence. If I'm trying to maintain my innocence that mu is 35 miles per hour within the speed limit, but they have a whole bunch of sample data that says, but you hit 45 on Monday, you did 52 on Tuesday, 43 on Wednesday, and so on, they're going to calculate a sample mean, sample standard deviation S, do a test statistic and see, is this more reasonable based on what my claim here was? If they get enough evidence, enough data against the null hypothesis, they reject this statement in favor of the alternative, HA. But if they don't get enough evidence, maybe they said on Monday, Mike did 36 miles per hour. Tuesday, Mike did 37 miles per hour. Wednesday, Mike did 35 miles per hour. All those values are equal or above. That might be not enough evidence to say that I'm really doing on average greater than 35 miles per hour. Because there's variability in data, they have to collect enough evidence against me. So part of the goal that we're going to be looking into section 5.1 is just setting up these hypotheses. And then in sections 15.2, 15.3, they've been glommed together. We're going to see how to categorize that evidence, how to reject the claim of the null hypothesis in favor of the alternative. So that's the kind of like 4-minute recap of what we were doing a week ago. Any questions about either of these hypotheses or the goals so far? Okay, then we had to hit this wall of text. First, we're going to come back to the hypothesis test conclusion. Specifically, once we go to make those conclusions in the very next section, we can either reject the null hypothesis or fail to reject the null hypothesis. But the reason these are the only two possible conclusions is because of this warning we'll come back to. In hypothesis testing, just exactly as in a court of law, we can never ever conclude the null hypothesis is true. If we did make that conclusion, it's literal circular logic, because one of the things that we do immediately when we form a hypothesis test is, scroll back up just one more time, the null hypothesis is initially assumed to be true. If you make that assumption, you can't conclude on true. We're just trying to see how reasonable is the data after making that assumption of truth there. So the actual mechanics of hypothesis testing, they start right here. You have to know exactly what is your parameter. This is the part of the content on the third exam. We had to write down what our parameter was when we did our confidence interval estimate on the very, very last problem. Once we know what our parameter is, we look to the question to decide which test are we actually running and what comparison are we making? What is a hypothesized value in the problem? So example 1 just has 4 different scenarios of looking at this idea. But there's so much to say about this kind of stuff. So let's add some words that you're going to hear a lot in the reading, lots of things that we'll say as well as we run through these problems. The greater than sign there is something that we're looking for in the context of the problem. Something is going to tell us in the problem that we're running this test, and the greater than tells us that this is called specifically a right-tailed test. That's a weird name, giving something a tail when we say that. But what it's coming up to is we're going to be looking at the right tail of a normal distribution, conceptually doing chapter 5 all over again, calculating normal probabilities. And those are going to be the probabilities we use to decide if we're rejecting the null hypothesis or failing to reject it. The less than sign here is the left-tailed test. And the really, really important one is when there is a not equals here. This one's called a two-tailed test. What makes this important is this is the default hypothesis test alternative. So let's call this the default test. The reason it's a default is if we find nothing in the context of the problem that says we're looking for a greater than direction or we're looking for a lesser than direction, if nothing of that's been indicated whatsoever, then we always default to this one. If we're just not sure, that's usually a best guess as well. So the two-tailed test is kind of the gold standard for hypothesis testing. Something in the problem has to direct you to either ones above. So there's 3 alternative hypotheses, 3 things that the researchers are trying to show. That whatever your parameter is, it's either greater than, less than, or just different from some hypothesized value. Hypothesized value comes from the context as well. And the null hypothesis, mercifully, is just one statement, that the parameter is itself equal to some hypothesized value. Well, the hypothesized value comes from the context, but another thing to mention is the null, H naught, is the only one with equality. So we're mentioning that equality right there. We write directly equals when we say the null hypothesis. Some textbooks might put in a less than or equals to match up the greater than sign, or a greater than or equals to match a less than sign. But in our textbook in section 15.1, we're always going for just directly equals. That kind of simplifies things a little bit, and there's really good reasons for doing that as well that we'll discuss later on. So this is the setup. These are what our hypotheses are going to look like. First thing we do is read through the context, try to determine what is the hypothesized value, what is the parameter, and what direction, what test are we actually going to do? So example one is just 4 different scenarios. This is pretty similar to the MyLab statistics problem of just doing that setup. This is the tricky part about starting out hypothesis testing, but there's a lot that's familiar here. So let's start it off in example 1. It says, for each of the following situations, define the parameter using the context. So that's, again, the tricky thing about statistics, but we've been working and focusing on this a lot. Once we know the parameter, we will write the null and alternative hypothesis in terms of that parameter value. But we also have to get the hypothesized value, so there's lots to work with here. But these are really small situations. So that's going to allow us to kind of laser in on what the context is. It's not saying a lot. Seatbelt compliance in Massachusetts, we're told, was 65% in 2008. The state of Massachusetts wants to know if it has changed. First thing we have to decide is, what kind of data is this? Is this categorical data or is it quantitative data? That's going to tell us what does a parameter look like. Is it P or is it mu is the big question here. And I would say this is the giveaway. 65% is the only value that was given. It didn't give us a unit. There's no time, there's no, say, age, there's no distance, just a 65%. This tells us this is categorical data just by this right here. There's only 2 outcomes, success versus failure. A success looks like the thing the data is talking about. The person, the random driver they selected is seatbelt compliant, or just any driver in the population is seatbelt compliant or not. So we can say it's categorical, it is success failure data, and the success is seatbelt compliance. So that step is critical because it tells us right out of the gate, parameter is P. So we know what the parameter is going to look like. It's P, but we have to define the parameter using the context. And like we mentioned before, it's not always easy. We've taken a lot of time with this and we'll continue to do so because it's one of those skills that you just get better at over time. You have to practice it a lot because there's lots going on with statistics. So let's do that very careful practice again on this. First thing to note though is P as a parameter is not 0.65. It's a population proportion of successes in the entire population. But this is data way back in 2008. One thing we've mentioned about populations is they absolutely will change over time. So seatbelt compliance in 2025, no guarantee it's what it looked like in 2008. That was a different time. Feels like a very long time ago at this point. We're getting to nearly 20 years ago. Still, that 65% is important. That's a hypothesized value that we're thinking about. We're wondering if it's changed from 65%, but that's a pretty big giveaway. 65% is, actually, let me use a different color from blue here. That's a null hypothesis. The 65% is P naught equals 0.65, hypothesized value. It's a population parameter as it was way back in the day. So now knowing that, we can say P is the true, well, let's say it, we could say true proportion of successes, but we usually said population proportion of, we can't say successes if we're writing out the context. We have to say what the success is. So we'll say true population proportion of seatbelt compliance that's the success. Now we write out the population among all Massachusetts drivers and we're not talking in 2008. We need to be time specific. So let's just say, who knows when this is being redone? We can imagine 2025. So you can say 2025. Let's just say currently. So we're wondering how many people are seatbelt compliant currently in Massachusetts. P is going to give us a percentage or proportion telling us what that is. So here's the layers that we are peeling back. We had to know if it's categorical or quantitative. Once we found it's categorical, we know it's a parameter P, so we wrote it out in context. But we're avoiding the 2008. That's the hypothesized value that's going in. And this much so far allows us to write out our null hypothesis, H naught. H naught is the statement that the parameter, in this case it's P, is equal to some hypothesized value, and that hypothesized value is 0.65. So the null hypothesis is a statement of nothing's different. 2008 to 2025, they're exactly the same as far as seatbelt compliance goes in Massachusetts. It's like a statement of not guilty. It's a statement of the status quo is maintained. No changes happened whatsoever. Let's say it that simple way. The null hypothesis is a statement of no change. So we've got the null down. We're going to test the null against or versus an alternative hypothesis. Here's where we probably, especially in a longer problem with more context, this one was just 2 sentences, definitely reread that context. Seatbelt compliance in Massachusetts was 65% in 2008. State wants to know if it has changed. This is the research question. This is what we're trying to establish. Is 2025 different than 2008? We're trying to say, which test are we actually using? That's going to be the alternative hypothesis, HA. It still includes the parameter, so P is still there. Includes the same exact hypothesized value. So if you used 0.65 once, you'll use it again right here. The major thing we're trying to decide is, which one of these are we actually using and why? It's in the context. Anyone see by the statement of part A which test this is? Are we looking for seatbelt compliance has gone up? Are we looking for it has gone down? Are we looking for the two-tail test? Anyone see which one it should be? Yeah, absolutely. The buzzword is right here. The state wants to know if it has changed. That's the not equals two-tailed test. If it was worded, the state wants to know if it has gone up. If there more drivers are buckling up in 2025, we'd have used this one, the greater than. Or maybe they suspect it's gone down. Who knows what's going on in Massachusetts? I don't know much about that state or its drivers. But if we are using the left tail test, using a less than here, they would have had to set in the problem very specifically, the state wants to know if it has gone down. But when it says has changed, it implies directly two-tailed test. Alternative hypothesis is that in 2025, or just currently, the proportion of compliant drivers in this state is not 0.65, not 65% compliant. Well, that's our first run at it. We're going to practice this a lot more. And when we go to the next section where we're completing the entire test from start to finish, this is the first step. Well, step 1 is really the parameter, but then the next step is just to write down your hypotheses in terms of whatever you said P was at the very beginning. Any questions at all, folks, putting those ideas together at the moment?
Does that say hypothesis is equal to P. So are those two little dots you made, are those equal signs?
These two dots here,
Yeah.
more just a colon matching, let's say that colon up here,
Oh, gotcha.
kind of like an equal sign, but really just saying the null hypothesis is the statement of that. So just matching up the format here to
Gotcha.
here.
Thank you.
You bet. Other questions at the moment?
So the blue piece is the parameter. Right?
Yeah, I also put it in as a green P because I'm color coding more the alternative versus the null, the way I color coded it. So the same value P that was you indicated in the null also goes in the alternative. And just to make that more apparent, wouldn't hurt to smack these with the highlighter as well. Other questions at the moment? It's a lot of ideas that go together all of a sudden just to put down a hypothesis test. The good news about this is it's really, like we mentioned before, two sides of the same coin. Hypothesis testing and a confidence interval estimate are really doing the same kinds of things. This is just a direct way to say, what is the research question itself? How do we write it in the state of the parameter? And if we rejected the null hypothesis and said, we have evidence that this alternative hypothesis is true, the very next thing we would do is estimate P. You wouldn't end a study like this by saying, yes, the state's found evidence, it's not 65%, because everyone's going to ask you, well, what is it then? And at that point, you provide the confidence interval estimate. So hypothesis testing and confidence intervals, they all go together really. But for the sake of practice, here's our next look at this. I'll paste this above just because we're still learning these ideas. Here's our reference chart for what the hypotheses look like. Most of these, just to be upfront, are categorical data because that's what our next section is going to be about. But one of these parts is going to be quantitative, so we know what that looks like when we're in the section 15.4, the last one of the semester. But just going through those thoughts, the percentage right here is another giveaway that this is categorical data. Which means parameter is P. But when we look at that, again, let's keep a keen eye at that 45%. Let's see what this problem is all about. It says last year, so imagine that's 2024, a survey found that 45% of the employees were willing to pay for on-site daycare, so less than 50%. The company wants to know if that has increased this year. These scenarios are made up just to make them as simple as possible so we can really focus on constructing the hypotheses. But that 45%, well, that's the proportion of the population, all employees, willing to pay for on-site daycare in the prior year. That's no longer the parameter that we're really caring about. We care about the parameter as it is in this current year, whether it's gone up or down. Well, more about increased, it looks like. That tells us the 45% in this problem, that one is the hypothesized value. So way to write that out is P naught equals 0.45 is the hypothesized value. And notice we're writing it in a kind of a funny way. P sub 0 for the P naught is kind of strange looking. There's a good reason for that. This is going to be part of the formulas when we go into the very next section, when we do the full hypothesis test. So that symbol P sub 0, P naught, kind of a reminder that it's here in the null hypothesis, but it's also in the alternative as well. So there's our hypothesized value. The parameter that we're going to put down, P itself, is going to be, well, this is categorical data with successes and failures. Being willing to pay for on-site daycare is the success, but we're talking about this year specifically. So putting those two together, we can say P equals the population proportion of employees willing to pay for on-site daycare. So that's what the success is. We have to mention the population somehow, but that would be just say all of the employees in the company, but in the current year specifically. So we'll say among all employees, in this company currently, or this year, you could say. Let's say it that way, they say it in that context. Let me go with all employees in this company this year. Okay, we've got a parameter down, so that's the part highlighted in yellow. And I think I forgot to highlight it in the last one. Let me make sure I do highlight that just to convey that thought. So now that we have the parameter, we know where it's going. It's going in the null, it's going in the alternative. The hypothesized value, I'm running out of color, so I just wrote out hypothesized value here, is the 0.45. It's the thing we're comparing it against. So now we can write out the null hypothesis. That's the one we're putting down in blue. The null hypothesis is now the statement that that same parameter P we wrote down hasn't changed at all. Still exactly 0.45. Yellow just to convey, P is referring to that same parameter. And again, this is what makes statistics kind of tricky. A lot of times there's more than one population on the table. This is kind of a time population. There's a temporal component. There's the population as it was last year. That's where the hypothesized value came from, the 45%. But then there's the population as it is now in the current year. That's where the new parameter P comes from. Sometimes it's not a temporal component. Sometimes it could be geographic. Maybe we're comparing one state against another state. Maybe it's a crime rate, or maybe it's something nicer to think about. Other examples along those lines. But time seems to be a common one, it looks like in these parts at the moment. So we have an alternative, we have a null hypothesis. And let me fix my screenshot because I circled the not equals on that one. Not every one of them is a two-tailed test, so let me get the screenshot without that part circled. That was meant so that we didn't have to scroll up and down a bunch, but scrolling one more time. Here's the statement of hypotheses that we're considering. We're going to test that null against, or you could say versus, and you don't have to say anything at all between them, but that's just colorful language that often goes in when you write this out. Here's HA. Parameter P goes right in the start. Follow the color coding above with what the alternatives look like. Hypothesized value goes in as well, so 0.45. And then something in the statement of this problem is going to tell us which one of these are we actually using. Anyone spot the test? Left, right, or two-tailed?
Sorry, what's your question? Increase, so they want to know if it is going to be bigger, so the top one.
Yeah, good call. Right here, what it says, the company wants to know if it has increased. That's it. Really, just the word increase itself is the only thing that tells us which test it is. So just like you said, it's the greater than right tailed test by that word alone. So here's what we test in the alternative. The alternative hypothesis is, again, the whole goal of this research. You're often looking at a question, even if there's no question mark there, there's a question implied. The company wants to know if it has increased this year. The research question is, has that proportion gone up? So the whole goal of the study is what the alternative hypothesis is right here. If you read out this alternative hypothesis statement, it would say P. We define it above, the population proportion of employees willing to pay for on-site daycare among all employees in the company this year is greater than 0.45 or 45%. So the whole goal of this study is encapsulated right there in the alternative hypothesis. The null hypothesis is just a statement that nothing has changed. It's still 45%. If we're comparing at time, we're saying nothing's changed from one year to the next. If we're comparing in location, say one state to another, one country to another, we're saying everything is the same across the border. So the null hypothesis, statement of no change. But let's say here for the alternative hypothesis, this one is essentially the research question. The research question itself is always contained in the alternative. So when you read the context, imagine you are the researcher. A bit of role playing kind of gets you in the mind of who's doing the study and why. And if you're the researcher, you have to agree that the alternative hypothesis is what you're really trying to find out in this study. If you can agree on that, you probably have the right alternative. Well, that's another look at these kind of problems. We have two more to take a look in because I feel like this is tricky enough. It's good to spend a good amount of time discussing these. Any questions or comments at all, folks, on how part B went? Okay. Again, the giveaway is the 45% tells us categorical data. It's success failure data. A success is being willing to pay and a failure is not being willing to pay. And there's another percentage on this one. Sorry, it's kind of redundant. Probably should have mixed these up again. I do have one that is quantitative data. That's going to be our last part, part D. Let's take a look into this one carefully, just for the sake of really seeing what can happen on these. We had the two-tailed test. That was a statement. We want to know if it has changed. Has increased was the right-tail test. Now let's read through this one. Regular credit card customers have a default rate of 6.7%. I wonder how old that data is. I bet it's changed in 2025. A credit card bank wants to know if that rate is lower for their gold card customers. I guess people with a higher credit limit is what they're referring to, or just whoever decided to sign up for their new contract. But you know where it says the credit card bank wants to know if the rate has, or the rate is lower. That one word right there, lower, tells us the test. We're testing this lower rate. So this makes it a left-tail test just from seeing that one part of the context. So this is going to be a less than in the alternative, less or left tail test. So that starts us out. And interesting how they started the problem. They said regular credit card customers. I'm not sure if they're talking about the own company's customers or just say every credit card customer in the entire United States of America, an entire national value. But either way, the percentage here tells us it's categorical. So parameter is P once again. And it's again success failed data. It says a credit card company wants to know if that rate is lower. And they're talking about a default rate. That sounds like that's the success in this problem, defaulting on your credit card. Remember, success is not always a good thing. It's just the thing that we're focused on studying in the problem. So defaulting on your credit card is the success in this problem. Even though that sounds financially terrible, really bad news. So success is there. And 6.7%, this is just the hypothesized value. The part that's going to go here and here. So P naught equals 0.067 is the hypothesized value. So it came from here, 6.7%. But notice we're being pretty specific how we're writing this down. 0.067, and that's actually really, really important when it comes to hypothesized testing. This was the same kind of deal when it came to confidence intervals. In confidence intervals, when we went out to write p hat, the sample's proportion of successes, it couldn't be a percentage. If it was a percentage, it could cause problems in the standard error in the whole confidence interval method's last step as well. And even right here, when we go to write out P naught, notice each time we wrote it down, we converge from a percentage to a decimal number, just like in the last problem. So same here, each time you see a percentage, if you're starting to write down things like P naught or the null hypothesis, alternative hypothesis, here's just another big reminder on this. Must be a proportion for formulas. We wouldn't get in trouble if we put in the percentage and the hypotheses, but it's going to cause us to get really mixed up on just the very next step if we use a percent rather than the 0.067. So with all that on paper, we can write out the parameter here. If a success is defaulting, but the credit card, this is what they want to do. They want to know if the rate of default is lower for their gold card customers. It's changed the population from apparently either the company's own credit card users or everybody in the USA to just the company's gold card customers. So P now is the population proportion of defaults among this company's gold card customers. So we've got a parameter down. Any questions at all, folks, writing down P for this situation? Okay, once you've got a parameter down, really, you just have to know what shape does the null hypothesis take, what shape does the alternative hypothesis take, because we have a lot of this down. The null is going to be a statement, P equals. The alternative is going to be a statement, HA, P. Well, we'll decide on the test. We kind of know it's a left tail test. But the hypothesized value just goes right into both of them. 0.67 goes here. Let me try again. 0.067 goes here. 0.067 goes here as well. So whatever your parameter P was, it drops into those three spots. Again, still following the color coding very specifically. The last thing that's tricky is deciding what was the test in the first place. When it said lower, they're thinking that somehow their special gold card customers default less often, less than 6.7%. So we put less than here, doing the left tail test for this particular problem. So even though it's just 2 sentences worth of context, there's a lot of thinking and writing and putting things together in just the right spot. So we'll be practicing this again a lot, again in section 13.3, the very next section. We'll be doing it all over again in the last section, not 13, but 15.3, and in the last section, 15.4, when we do this for quantitative data. Well, any last questions or comments, folks, before our last one, before we change examples? Okay, pretty much the MyLab statistics homework is this kind of stuff. Just really good practice of determining what the parameter is, determining the null alternative hypothesis. So one more run. Part D says regular credit card customers have been with the company. Sounds like it's the same context as before, but the data is different. These customers have been with the company for an average of 17.3 months. There's a really big giveaway on what the data type is on this problem. The moment you saw the word average, that's a huge giveaway. It looks like we're looking at quantitative data. And also they gave us another number with a unit, months. That's another big giveaway. So these data are quantitative. There's no categories here of successes or failures. There's just a length of time. How long have these customers been with the company? So the fact that it's quantitative, it's conveyed through they said average, and also the fact that months was given as well. The lack of percentage is not the best indicator because you could take the percentage off of this and just call it 0.067 and it's just a number like before. But the fact that the number is bigger than one, that's another giveaway. It's probably quantitative because a number bigger than one can't be a proportion or a percentage any longer in these contexts. So we've got quantitative data. What that tells us is that this time the parameter is mu, the population's mean this time. So that's our big dichotomy. We looked at this way back in, say, chapter 1, I believe, categorical data versus quantitative data. And here's where it's starting to really take effect. We need to know how to formulate our hypotheses based off what is the parameter in the very first place, and knowing the data type tells us. So rereading the context again, the regular card customers have been with the company 17.3 months on average. The credit card company wants to know if their gold card customers have been with the company on average the same amount of time. So that's the whole statement of the problem. That tells us the hypothesized value this time is the 17.3 months. But we won't write P naught because the parameter is mu. What we'll write is mu sub 0 or mu naught equals 17.3 months is the hypothesized value for these data. Okay, so we're nearly there. Let's decide what kind of test that we're going for. If something in the problem says greater than, we're going to go for the right tail test. If there's a less than indication, we'll go for the left tail test. Or it could be a two-tail test. Anyone see which kind of test this one should be by the context of the problem? Let's think about it. There's got to be something somewhere in this context that's going to say one of the three. Yeah, go ahead. Yeah, absolutely. What would you say the giveaway was for the two-tail test on this one? Yeah, exactly. There's no direction there. So good eye on this. But it said the same amount of time. They didn't say for a longer amount of time. We might have assumed that our own, that somehow gold card customers are special, but they're not even testing for that. They're not testing for if it's a lesser amount of time than the 17.3 months. They just want to know, is it the same? So by the wording there, we would put in not equals, it's a two-tailed test. The wording there is actually really tricky, so we're going to come back to that before we finalize this problem entirely. But that does tell us the right test to use. So now we can go through the motions. We need to write out what is the parameter specifically, the thing that's being highlighted in yellow in all of these hypotheses. We know it's mu because the data is quantitative, so we can start by writing out mu is going to be equal to the population. And this kind of hurts our brain a little because we've been saying population proportion, but that's not the case anymore. We need to say population mean, or you could say population average, the same concept. I'll go with mu as the population mean. Then you have to mention what the data is. It's months, so mean amount of months. So mean amount, I'll say time. Let me make it grammatical first. Mean amount of time in months. Well, what's going on with that unit? It's amount of time that customers have been with the company. So we can say that customers have been with the company. And it's still not the full story because we just mentioned what the quantitative data even is. The amount of time that the customers have been with the company, but every parameter has rolled into it at the same exact time what the population is. The population is all the gold card customers for this company. So we have to mention that as well. So we'll say for all gold card customers for this company. So we finally got the parameter down. The context in part D and the other parts are so small that it feels like the parameter is just as long when we went to write it down. But with all that down, that's the part in the hypothesis testing diagram we have above that's highlighted in yellow. We can start now just writing down all of our hypotheses in one shot. Null hypothesis is the statement that mu has not changed, whether we're looking at regular customers or the special gold card ones. The population is essentially the same with respect to average amount of time they've been at the company. So mu equals 17.3 months. So mu goes there again. And then the next one, HA, is the statement that mu, and I'm in the wrong color. We're using blue for the alternative. Let me try to fix that real quick. HA is the statement that mu is not equal to the hypothesized value of 17.3 months. You don't have to put the units in, but if it's quantitative data, it's probably a good idea. It's going to make conclusions a little bit easier when we get to the last step when it comes to hypothesis testing. We did it, folks. That's our last hypothesis to set up on example 1. We'll take another look at this when we go to the next section. But any questions or comments so far at the moment? Okay, there's one thing that's really dangerous about this problem. It goes back to what we were saying initially when we were starting to talk about hypotheses. There's only 2 possible conclusions to hypothesis testing. You're either going to reject the null hypothesis in favor of the alternative, or you're going to fail to reject it, and it really is one or the other here. The big warning is we can never give a conclusion, no matter how tempting, no matter how pretty the data looks, that the null hypothesis is true. So when we look at how we set up the last one, it is concerning with what was being asked. It said in part D, the credit card company wants to know if their gold card customers has been with the company the same amount of time. It's as if they're asking us to show the null hypothesis is true. And whoever does the statistics for this company needs to alert them, we cannot do that. We can either show that the population mean amount of time customers have been with the company is either not equal to 17.3 months, that's when we reject the null, or we'll fail to show this. We'll not have data in support of this conclusion. But we can never come back and say our data shows and proves that the gold card customers have been with the company the same amount of time. We can never show the null hypothesis itself as true, and that was the gargantuan caution about hypothesis testing. So part D is a weird one. Sometimes the research question is posed in a way that's actually incompatible with the conclusion we can write. Still, it was talking about a two-tailed test. This is the right alternative, H sub A. Let me fix that A. It looks like a O down there. That's a better looking A. So here's the next big warning. we cannot write a conclusion H naught is true. And that's the big red flag. If you ever do statistics for someone, no matter how much money they try to pay you in consulting, that's a huge red flag if they try to ask you to do that. It cannot be done in statistics with hypothesis testing whatsoever. The sciences just can't support that. We can find evidence in the direction it may be true, but there's no proving it. So that's what makes Part D kind of a weird one as a one-off. Really just a reminder, you can never conclude that null is true. We'll come back to that because that's going to really affect how we write out our conclusions. Our conclusions, we'll come back to this table again, can only be these two different statements. Well, we did it, folks. Those are the simple scenarios for setting up hypotheses in both of these problems. We're really kind of satisfied with the way the homework is going to look in the section 15.1 in MyLab Statistics. It's going to be small, quick contexts like these. But the reason I have one more problem on these notes is these statements are so quick that it feels jarring when you go to the very next section. We know statistical problems usually have a lot of context. There's a lot more to filter through than just two sentences like we see here. And so that's what the next example is more about. What does a real problem actually look like? Probably not as short as this one. Well, any questions or comments at all, folks, before we go to take a look into the next problem? Okay, let's take a look into that one next and see what's going on. So this one is a full-on study next. Let me bring that up. So we're looking at something for education statistics on example 2. This will be the last one for the notes. It says the National Center for Education Statistics monitors many aspects of the elementary and secondary education nationwide, probably talking about USA. Their 1996 numbers are often used as a baseline to assess changes. I'm not exactly sure why that is. Maybe things were going great in education back in 1996. Who knows? Or maybe the study done was very, very comprehensive in 1996. Nonetheless, those 1996 numbers are a baseline value. Baseline's kind of a giveaway, though. The null hypothesis is a statement of not guilty, the status quo, that nothing has changed. The null hypothesis is a statement of baseline values. So when they said baseline right there, that means this number is probably the hypothesized value of the whole problem. 1996 comes up again. In 1996, 34% of students, sounds like they're talking about elementary, secondary education students, had not been absent for school even once during the previous month. Well, because 1996 is the baseline numbers, that value, 34%, is probably the hypothesized value. Let's keep on writing or reading out this just in case we can change our mind on this. Now it says from 1996, we're looking into data in year 2000. In a year 2000 survey, responses from 8,302 students, that looks like a sample size, n equals 8,302.
Can you scroll up?
Yeah, absolutely. To about here.
That's good. You scroll back.
Okay. So that n equals 8,302 students show that the figure has slipped to 33%. Now it's getting foggy because there's like a cloud of numbers, right? There's the 1996, 34% had not been absent from school even once in 1994. In year 2000, we have a sample size, but that sample size has a percentage attached to it. We know that's a statistic, right? Whenever some number describes a sample, 8,302, that number itself is a statistic. Just trying to come up with a good color to use. I'll use black again. So 33% is a statistic, and this is categorical data where success is not being absent even once in the prior month. it tells us that p hat equals 0.33. It's the sample proportion of successes. This part right here is the success. So it's categorical success failure data, and this is the success. That's kind of tricky though, the 8,302 giving you another percentage. We had to know it's sample data giving us p hat right away in that problem. Well, let's keep on chugging through the context. It says next, officials would of course be concerned if student attendance declined. Now you might say, well, it was 34 in 1996. It's 33 now in our random sample. Well, not now, but year 2000, almost 25 years later. That's not evidence of a decline though, because we don't know what the variability is. So we would have to test that. If that statistic gives us statistical significance of a decline. But you know, when they mentioned decline, that's pretty important as well. Sounds like they're talking about a left tail test and hypothesis testing, because this is the whole research question now. Did this percentage go down in year 2000? So this word right here is a buzzword for a less than left tailed test in the problem. So now here's the instructions, same as the last example, just more context. Define the parameter using context, state the null and alternative in terms of that population characteristic. That's a weird wording here. I think what I meant to say here was parameter. Well, a parameter is a characteristic of a population. I feel like it's just worded weird on this one. Let me throw this in just as a clarification. So that means 34%, the baseline number, really is the hypothesized value. The data is categorical, so we'll say P naught on this one rather than mu naught. P naught is 0.34. Has to be written in as a decimal number. And now we've pretty much got it. Putting all that stuff together, let me match up the same color coding. The null hypothesis, let me cheat to make sure null is in green. It's weird to change that in the notes, so let me fix that. The null hypothesis is the statement that P equals 0.34. Alternative hypothesis is the statement that P, it's a left tail test, so we put in less than 0.34. But this is not quite good enough. This isn't done just writing these two down. We went through all the last steps of the hypothesis test. The conclusion is actually really hard to write down. And I've kind of tested this out all on my own. Back in the day when I used to teach statistics, way back in year 2015, a while ago, I never asked for this part. And hypothesis testing was really, really hard in those classes. People had a big trouble with the conclusion. Then I made a change right around year 2017. I started putting this into every single question, just like the conference interval problems. And I found if you just write this down, it gets into your subconscious. It's the same exact value that goes right here. And it makes the last part, the biggest punchline to what we're doing in this whole problem, the practical conclusion, tremendously easier out of nowhere. So this part is probably the most important part of the whole problem. Defining the parameter tells your brain exactly what you're going to do, makes the conclusion easy, and makes these look less mysterious, and will give you confidence if you made a mistake or if you stated it correctly. So this really should be done before the hypotheses. This is kind of bad modeling to put the hypotheses down first. Let's say what P is exactly one more time. We have to bake in the success, not been absent from school even once during the previous month. But we have to reflect that the population is all students in year 2000. We know it's secondary and elementary nationwide, so we could just say all students in the nation and not have to mention every bit of the context. So P in both of those hypotheses is the population proportion of students. And then kind of a weird statement, that have not been absent from school even once during the previous month. This parameter probably depends on the month, right? If it's January, that could be a weird month because December probably has more absences than maybe August, for example. But let's just write it out as they gave us the information, that have not been absent even once in the last month. Here's the population for all students. Nationwide, just copying the way they put it in their language. And that's what the hypothesis setup would look like for this problem, example 2 here. Feels a lot more overwhelming when you throw in just more honest looking context, real data. There's more numbers we have to filter out, sample sizes, statistics. A hypothesized value versus the unknown parameter is also a big conflict. But we'll be practicing this essentially all of the notes in section 15.3 for categorical, 15.4 for quantitative. Well, this section was all about just setting up those hypotheses. Does it make sense to folks about how it goes, or does it still feel kind of foggy and vague? How you all feel about it? Is it weird or not so bad? Glad to hear that. Looks like most of us are kind of on the fence about it. It's kind of one of those things where you're going to get a good feel for what it's like when you try it out in the MyLab statistics or when you try it out as a quiz problem. Well, let's save this up. We don't have a lot of time. We have enough time to take a look into what does the rest of the hypothesis test even look like. It's kind of cool because you go back to section 15.1. Out of nowhere, z-scores make a gigantic comeback, and it kind of tells us why we covered z-scores. Even better, section 15.5.4, sorry, getting my numbers mixed up, makes a huge comeback as well. The major thing we're going to be looking into is normal CDF. When we find evidence, when we collect data, we're going to use the, not inverse norm, but rather normal CDF to get our so-called p-values from the normal curve. This is what a left-tailed test p-value would look like. Left-tailed test just meant the probability or the percent under the normal curve came from the left tail. So that's where that connection comes into play. We just have to know how to get these numbers down below. They come from the z-score. Just as a reminder, a z-score is a data value where you subtract the mean of the sample, divide by a standard deviation. We can change that up a little bit and put in slightly different things. We also need another chapter, the central limit theorem for the proportions. So let's put this on the table as well. When we say sample mean, what we're really talking about is that mean is going to be the mean of the sample, p right here. The data value is going to be p hat, and the standard deviation is going to be this exact standard deviation right here. We're putting these two sections directly together, and here's what it looks like as finally an actual preview. Let's open up 15.3 with these thoughts from way back in the day, back in our subconscious. We have the central limit theorem back on the table. Everything you see here on this first page is just a review from what we did in chapter 13. The definition of p hat, the parameter p that we've been defining in our hypotheses, and a reminder about the central limit theorem. The central limit theorem tells us when we go to actually calculate p hat in any study, after we've taken a simple random sample, it came from another normal distribution if our conditions are met. So that's why the normal curve is back on the table for us in this situation. The mean of the sample is unknown, it's p. That's okay, we can still calculate a z-score. we'll use standard deviation p hat. And even though p is unknown, there's a reason why we can calculate that z-score. Recall the very first thing you do in hypothesis testing in 15.1. Let's go to the very top of the notes. The very first thing you do in a hypothesis test is you assume the null hypothesis is true. It's the truth of the population. But if you make that assumption, here's a null hypothesis. Assume this null is true, and you know the value of p. Truly, it's unknown altogether, but as we proceed through, say, a court of law or hypothesis testing, we temporarily assume p takes on the value 0.65, like in this problem. So that's the big connection. We will know what p is when we assume the null hypothesis is actually true. We will also know the standard deviation. With those two components, here's the new material. We can calculate a full-on z-score altogether. So this is just a restatement of the z-score. And here is the hypothesis test method. We have two hypotheses, the null p equals p naught, a two-tailed test here. It works for a less than, a left-tailed test, and a right-tailed test. But we want to state it once so it doesn't get out of hand right away. We're going to test at a significance level alpha. We'll come back to that, but that's our benchmark for evidence. We want this to be a low number. Much like we want confidence to be a high number, the z-test statistic is nothing but a z-score. It's p hat minus p naught, but p naught came from here, that exact null hypothesis. That's why when we were in 15.1, we wrote these out as p naughts. They go right here in the z-score formula when we go to calculate the hypothesis test. We assume the null is true, so we have an actual value. Then we just divide by the standard deviation. But we know what that standard deviation is now. It's this thing, square root of pq divided by n. But that p is p naught again, so it becomes p naught. 1 minus p naught is the q, 1 minus p naught here, divide by n. So in hypothesis testing, all we are really in fact doing is computing a z-score. This is going to tell us how many standard deviations is the sample data away from the hypothesis value in terms of the true standard deviation when you assume the null hypothesis is true. If that's a lot of standard deviations, your picture is going to look like this. There's going to be a tiny probability right here, and we're almost certainly going to reject the null hypothesis. If it's a small amount of standard deviations, the z-score is small, it's probably going to look like this as a picture. Your probability is going to be a large area, and we're going to fail to reject the null hypothesis. So this is how it all connects back. It's basically like just about the entire course in a certain sense. Well, really just chapter 5 and chapter 13 coming back in huge ways. Well, we can't get too far. We don't want to talk about it too much on the last 2 minutes of class, but we'll revisit all of these ideas, how the z-score formula, central limit theorem, null hypothesis, and the hypothesized value all connect back to that. Then we'll mention what the hypothesized value is all about, what typical ones are, just like what typical confidence levels are as well. Any last questions or comments? I assume there's a bunch of questions, but any last burning questions at the moment before we call it a night? Okay, we'll take a look into this tomorrow. It's going to be the hardest day to attend because I know we're right before the Thanksgiving break, but we'll do our best we can. We'll take a look into how this comes together, and we'll run through some brand new problems. This is finishing out the last problem, so I restated the parameter since we did it once. And then the problems down below are going to be brand new ones that we take a look into. Something about substance abuse, something about teens and distracted drivings, and another thing about crisis and civic education. This one's a really interesting one about knowing what the bills of rights are. Full disclosure, I would have been hard pressed to tell you exactly what the bills of rights were before I did this problem for the first time, but it's a fun one to do at the very end. We'll probably be finishing these notes when we come back after the break. So we'll be looking at this material here quite a lot. Well, any last comments, folks, before we call it a night? Okay, well, I'll see you all tomorrow. We'll be right back to it in this spot here. Have a great night, folks.
Do you teach any other math classes?
Yeah, I teach
Algebra?
algebra, intermediate algebra. I sometimes teach college algebra, but not very often. Pageant and Randy have it locked down on this campus. But then I teach the trigonometry class if you're taking trig and you know that. I teach another statistics class after this and then some calculus stuff, linear algebra stuff. Are you planning on taking a good amount of math classes for your program?
No. Not at all. No, I'm good.
Hey, you're pretty much almost done then by the sound of it. Congratulations.
Yeah. I never really did good at math, but I also too didn't really apply myself back in the day.
That's how it was for me in high school. Math was not my forte at all. I never did well in high school. I had to take some of the remedial math classes when I started in college, but then it just started to click in college for some reason.
But
Maybe I just liked my teachers better. Who knows?
I think you did a good job though.
Awesome. Glad to hear that.
I also, I pay attention to, because, I mean, that, and the combination really helps, you know?
Yeah. It's all about, getting through the class. It's usually more about what you do than what I'm actually doing. If you had a bad statistics teacher, but you're still working hard, you're learning it on your own and you're gonna make it through the material. It doesn't matter how great the teacher is, if the student, say, is just not paying attention, not coming to class, not doing any work,
Yeah.
they're pretty much screwed at the end of the semester, no matter what the teacher does at that point.
But I did, going through that stuff, it brought up a question about that quiz
Yeah,
that we just did, so. When I got my, the end. Right here. Those are the points that it's less, it's between,
yeah,
but that's what I got on the calculator, so that's not a percentage or a proportion,
that's correct. This one was quantitative data.
because once, yep, okay, it's just. It's clicked, it's there, we're
Awesome.
good. I'm not as quick on that, you know what I mean?
Yeah, it takes a lot of practice, actually.
Like, once you say that, then now I can associate it, but. I'm more focused on like getting the formulas and then putting the stuff right.
Mhm.
There's two parts, you gotta know what you're describing.
Yeah, that's a great way to say it. What kind of data is this in the very first place?
Formulas are the same, right?
Pretty much or close. The standard error is different, right? But
Little
it's
bit.
basically statistic, add or subtract critical number, standard error. Really the same kind of formula.
But, yeah, so, and that's why I don't do good with, I don't know, I don't do good with algebra, I still make zero sense to me, but.
Yeah.
Moving the decimals and stuff
Mhm.
to the proportion, like that's easy, but. Identifying when it is and when it isn't is just. That's why I always second guess myself,
Yeah.
so. Hey, we'll see you tomorrow.
Yep. Have a good one.
We're gonna,